Hello, my name is Lindy Humphrey. This is my Lab 6 Magnetic Molasses for Physics 2212. The introduction or purpose for this lab is to see and understand the physics behind magnetic fields and forces on magnetic dipoles. We use Faraday and Lenz's law in this lab. The purpose of this lab, what we do in this lab, is we're going to drop a magnet down a metal tube, measure the drop time, and then simulate the actions using a computational model, and in our case, this will be glow script code. A brief overview of the results includes the drop time average was 0.76 seconds, and the dipole moment we calculated to be 1.13 centimeters. And then main ideas and principles overview. Faraday's law is the induced electromotive force in any closed circuit is equal to the negative of the time rate of change of the magnetic flux to the circuit. The direction of the induced current is such that it opposes the change in magnetic flux that caused it, is Lenz's law. So basically the same formula as Faraday's law, but an opposite sign. And then the momentum principle is simply force equals ma. And then here's some pictures of our lab. This is what we used to identify what was the positive and negative end when we dropped the magnet down the tube. And then an overview of some of the simpler results before we calculated what we used to calculate the results. And then extra information, some assumptions we had. Air resistance is negligible. Only forces on magnet are gravity and the field on the foil. Some errors could have included incorrect measurement of time, radius, or length. Tube not completely perpendicular to the floor, meaning everything being human error. The system is the magnet. The surroundings is the rod and everything else. Initial conditions include magnetic north is pointed up and the initial velocity and time being 0. And then here's a brief overview of the code. I try to highlight everything that we needed to identify or what was changed depending on what units you had, what we had to add into the glow script code. And that's all represented here. And then here's the brief overview of the model that was created. In this computational model, the average time was 0.4630 seconds. Ours was 0.71, so obviously there was other factors influencing our model, and it was significantly shorter. And then one of the questions is, what if the resistivity of the conductor were reduced as close as possible to 0? How would the dynamics of the falling magnet change? Then the answer to this would be, there would be a high induced current and a larger magnetic force on the loop, causing the magnet to fall slow, or even slower than it did. And then the last question is, what if there was holes or slots cut into the tube? How would this affect the ring currents in your model? And then the answer to this would be, the holes would make the tube not continuous, so the induced current would be smaller, causing the magnet to fall even slower.